Thank you for the introduction. And also, well, before starting, I want to thank all the organizers for letting me speak today. It's actually, now that I think about it, it's pretty crazy to be here now in this day, especially. And okay, so well, and also let me thank the staff of IPAM for the very precise organization. So today I want to talk about the distortion. I will tell you what it is, and it's a work that we have put on archive a few months ago, last year, and it's joined with Marcel Bischoff, Ian Charlesworth, Sam Evington, and Dave Pennis. They're all here at the IPAM conference now, most likely. Okay, so what is distortion is, I tell you first what it does, and then I tell you how to define it. It's an invariant, well, up to star isomorphisms, and it's our way of solving rather, let's say, the most classical type of problem in this business of quantum symmetries, when namely it classifies inclusions of von Neumann algebras, this A inside B here. And now I will not enter in the description of all these adjectives here, because I will do it later when they are due. And I only want to tell you that the news here is that is this guy here. So, and that I'm considering inclusions that are not subfactors. They are like, these algebras may have a finite dimensional center. Second thing that distortion does is, well, classifying representations of unitary multifusion categories. And these were called by Makoto, they were called actions, if I remember correctly, in bimodules of a von Neumann algebra. And here, I guess we have seen already a couple of times the meaning of unitary, the meaning of fusion, and the new word here is multi. So multi means that I'm dropping the assumption on simplicity of the tensor unit. So the tensor unit now is a semi-simple, so is a finite direct sum of simple objects. Okay, so the question here is how to complete Popa's standard invariant, if you want to rephrase here this whole business, for multifactors. But the question I want to convince you first is that we have to see why this invariant is not complete for multi things. This was not clear to us at the beginning of the project. Okay, so this is more precisely the type of inclusions I'm going to deal with. They are inclusions A inside B of von Neumann algebras with the same unit. And they are, if you know this book, the Goodman, Delarp, and Jones, they are exactly those considered in chapter 3. Okay, there are two multifactors. It's a terminology that we gave for saying that they are just, so it's just a fancy way of saying that they are finite direct sums of two unfactors. These AI, Bj are two unfactors. And here, I only ask you to remember this notation here. The PIs will always be the atoms, so the minimal central projections in A, and the QJs will be the atoms in B. And this will come up a few times in these slides. Okay, second assumptions on the type of inclusions that we have is connectedness, which just means the intersection of the centers is trivial. And I think, again, in that book, for the first time, they show it's like a combinatorial thing. So they show that this condition here is the same thing as saying that the inclusion graph is connected in this sense. And two things about this: if you have never seen an inclusion graph, no worries. I will tell you some examples and it will become clear what I mean by inclusion graph, if it's not already clear here. And I want to say that connectedness is almost without loss of generality. So whenever you have an inclusion of algebras with centers, you don't want to reduce into irreducible subfactors, but you want to reduce into connected inclusions. Okay, and the last assumption that I always want to live with is finite index. Finite index, I think people have already introduced it in the workshop. Let me say, I don't give the analytic definition, I give the categorical counterpart. So I'm saying that the inclusion A inside B is a finite index if the standard bimodule, this guy here, this AB bimodule that I write as X, is dualizable. And dualizable has already been explained very well by Makoto and also by Andre, at least, and also in some talks yesterday by the students. And I just want to draw pictures. So I say dualizable if I draw the bimodule in a very schematic way, in this way, so with the bicoloring. The conjugate bimodule is the opposite color, and it's just the opposite Hilbert, the conjugate and Hilbert space. And finite index means the existence of these caps. So these colored caps that, in a sense, well, are telling me how X bar is, in some sense, a weak inverse of X. So they're telling me how the identities L2B and L2A in this tensor category are sitting inside here, and I'm asking these equations here. So the conjugate equations, or zigzag or snake, as you wish. Okay, standard invariant is something that we have already seen, so I will be pretty fast here. Standard invariant is a triple for us. It's denoted by like this, and it's the datum of a rigid multitensor sister category generated by our standard bimodule. We keep in mind that we have a generator, namely the standard bimodule, and we also choose some special solution of the conjugate equations that I have shown you before for X and X bar. Not any solution, there are many if you are finite index, but I also want to have this property here that the bubbles, the loops are numbers. They are the same equal number. And this is, of course, well, they are numbers for subfactors because the floating boxes like this one, they float, they have no legs, they are elements in the centers. And so I'm asking that these are the same element, the same scalar multiple of the common tensor unit, of the common unit in the inclusion. Okay, so why do I do this? Because I want to have Jones projections, and not only these ones. It would be easier to have these, because if I only have these guys to be invertible, then there's no problem in defining a projection, but I want to do planar calculus. So I don't want to have to bother where I put the inverse of this guy, in how many strands on the left and on the right, in which color. So this is just a very convenient assumption that you can make. But you have to say if you have solutions of this form. And we do have them, and we show in the paper that, and there is actually only one family of solution of this type, and for fusion, well, for multifusion. And in case you are not fusion, these well, solutions with this property here that is very important are called like standard solutions, and I'm referring here to a paper with Longo last 2 years ago. And well, they are not characterized by this scalarity property, as far as I know, in general, but they exist, and they are uniquely determined by unitaries. Okay. So that's the standard invariant, and here is our main theorem, which says that if I also assume hyperfinite algebras and finite depth, and which means, well, categorically that this multi-tensor category is actually multifusion, so it has finitely many simples up to iso, and then and so we have a complete classification. So we have a classification of this type of inclusions by means of the standard invariant, this category that I have described you before, and something else. The something else is the distortion. And that's actually a new piece of information. And that's not categorical information, is rather spatial or tracial information. Okay, so before actually telling you what is the distortion, I give you a bunch of examples of inclusions with these properties. Namely, when I give you like these examples here, I just consider inclusions of matrix algebras and tensor with the hyperfinite to one factor. They have all the properties, including finite depth, by a theorem of von Jones. And okay, so if you haven't seen this stuff before, I will give you examples. And the very first example that you can think of is already enough for motivating this. So which is the fundamental question, why the standard invariant is not enough in this case. So the example is the A4 inclusion, which is C plus C inside this M2 plus C, and it's described by this weighted graph, or by its Bratteli matrix. and with the spin vector here, the vector of dimensions. And I will tell you better how this inclusion looks like later on. But now here, let me say that the index can be computed out of the Bratteli matrix. And in this case, it is this magic number phi square. It's this irrational number, the square of the golden ratio that was found in subfactors. Okay. So now I'm taking the tensor product as before of this A4 inclusion times the hyperfinite one. And this was known to Popa already for sure in 1995, that this guy here does not admit an infinite tunnel. Why? Well, because the index is irrational. Okay, so in his terminology, it is not homogeneous. Okay, why is it interesting? This, well, because if I'm trying to classify stuff, the only hope we have now is, well, to run into his theorem. So somehow, so to go into the generating tunnel and use the standard, the usual machinery for subfactors. So if you're not homogeneous, so does not apply. But also we argue more. So we know that there is no other way of classifying this guy by the standard invariant. Why? Well, because we show that there is not a single downward basic construction for this type of inclusion here. And also we say that it is not determined by the standard invariant because, so that's, sorry for these comments here. It's easy to see that if you take, well, twice the standard, the basic construction, then it's easy to see that this inclusion and twice step above have the same standard invariant. They have the same representations, so they are Morita equivalent that we define, but I will not have time to talk about this for sure. But we show that they have different distortion. So we compute the invariant. It's very easy in this case, and it's different. So it's a star isomorphic invariant. They cannot be star isomorphic then if this is different. Or another more simple-minded way is if you believe that this guy doesn't have a single downward basic construction, this has two by definition. So once again, they cannot be star isomorphic. And this is the easiest example possible if you allow for centers. Okay, a second example, the second easiest example possible is the A5 inclusion that looks like this, is a C plus C inside this C plus M2 plus C with this Bratteli matrix and with index 3. This is looks very much like before, but this is very different. Namely, it is homogeneous. This we will see why. And in fact, it has no distortion. So the distortion is gone, is a standard. Standard means that there is nothing but category here. So the distortion in this case is determined by the standard invariant. Okay, so now I tell you what distortion is. A distortion for a dualizable AB bimodule, X. And for example, you can think of the standard bimodule if you want to talk about distortion for an inclusion. And so what do is just you cut down X with these minimal central projections, Pi on the left, they sit in A, and Qj on the right, because they sit in B. And you end up in having a finite collection of factor bimodules, AI, Bj bimodules. Okay, so you can define this whenever the cut down bimodule is non-trivial, is non-zero. So you can consider this ratio. So the square root of the ratio of left von Neumann dimension over AI and right von Neumann dimension over Bj. And so you may wonder, okay. So first of all, it's only partially defined because I didn't say anything if this cut down is zero. And so you may wonder why this ratio has more information than just the product. So the product is the Jones index. So why taking ratios is more sensible in some sense, so for the inclusion. And this is the whole point I want to convince you of today. Okay, so now I compute some distortion for this A4 inclusion. And this is the explicit form of the inclusion I have promised you before. So if you have this graph or the matrix is only telling you how to embed the lambda and mu complex numbers into M2 plus C. and that's the way. So you have lambda here, so you put it once in the first block, and you have mu, and then you can put it twice. So because you have two legs here, so you put one mu here and one mu there, and that's the inclusion. And for computing distortion, so which is this matrix here, and notice please the star where here there is a 0 because I didn't define it in that case. It's just here is just very easy. So you take the standard bimodule, so you cut it down on the left and on the right, and you end up with the C2. And then you compute this ratio of left and right von Neumann dimensions, and you end up in this 2, which sits here. So that's just the easy computation for this matrix. Okay, nothing else. And these are the minima central projections that I was using here. Okay, nothing else. Same game for a
question in chat. Stefan Voss is asking, you say that this distortion is not categorical, but isn't it a kind of a categorical dimension?
Yeah, well, good question. Good question. Well, as far, I said it's not categorical because if I convince you that inclusion having the same standard invariant may have different distortion, as it's just a computation that will come, then that's my explanation of being not categorical. But we thought about like putting distortion as additional data on the category, but then it becomes an enriched category. So I'm not sure. I prefer to keep separate, like category on one side and the distortion, in my mind at least, is on another side. But yeah, that's a very good question. So it's maybe it's just a matter of taste. I hope I answered to your question. I don't see the chat. No, I cannot see the chat. Well, okay. Thank you anyway. Okay, so this is for A5. For A5, the computation is pretty similar. It's this guy here. And with the two stars where I have no edge. And here there is a 0. And now I'm running a little bit fast. I want to pose you this question, which is not very motivated by now. I want to complete a distortion. So this is a partially defined matrix. I want to find the good way of completing it. Well, how can I do it? I just put these numbers here of distortion on this graph, and I complete it by closing loops. I just want to close oriented loops. So if I want to go from, well, complete first the bipartite graph from here to there with the 1, I can just go up with 2, down with 2. So I multiply by 1/2 and end up with 1. And then I put a 1 here because it's the product of 2, 1/2, and 1. Same thing on the other side. I may even complete it on the whole graph, so to have so what is in fact a groupoid homomorphism from the groupoid of vertices and into the positive real numbers with multiplication. Okay, so this is just my favorite completion by now of distortion. Okay, similarly for A4, this is just, I put the previous matrix in the inclusion graph, and I close loops, and that's it. Okay, now I said it very quickly because in fact this possibility of extending distortion is an interesting property, and it's interesting because it characterizes a property that we call extremality of the inclusion, so, and not necessarily multi-matrix inclusion. So now I'm taking a general inclusion of finite algebras with finite dimensional centers connected, and we give this characterization of when these are conditional expectations. This is the Markov trace one, the one of GHJ, and this is the minimal one. And when they are the same, so we say that the inclusion is extremal. Okay, so this is characterized by this property of extendability of the distortion modulo this equality here that I'm forgetting by now. Okay, so and let me just say here, for the sake of understanding what comes after in the talk, I go back to multimatrices where this equality is just the same. So in the next slides, I will denote the Bratteli matrix by D, that I call dimension matrix, because that's what it is. that's purely categorical in the sense it comes out of the standard invariant. And so just a change of letter by now. And also this possibility of extending distortion is the same thing in general as expressing distortion as a ratio of vectors uniquely determined up to a common scaling. And in the case of multimatrices, the vectors are just these dimensions. So that's a multimatrix inclusions with 1, 3, 2. That's my vector xi, this is my vector eta, and that's it. So distortion can be determined if you look at the inclusion graph and nothing else. Okay, so now for extremal inclusions, so we can continue the tower and go to infinity, and we get a sequence from the first one, which is a ratio by extremality. So we get a sequence of matrices like this. And what we show in the paper, well, is that so there is a limit point for the even sequence. And the limit point is given by this ratio here, this number. Okay, so this number is what we call the standard distortion. Standard because it has to be determined by category only. And in fact, these numbers here are the Perron-Frobenius data of this matrix dimension, or if you want here, Brattel inclusion matrix. So I take the left and the right, or the left for the transpose vectors. I normalize them L2, and this D is the L2 norm of the dimension matrix, and I take these ratios. Okay, so this limit is always the same. It is always given by this ratio here. Okay, so now let me show you that this theorem is in fact correct in the A4 case. In the A4 case, as I told you, so this is the tower. So this is the inclusion graph for the tower. This is the way you can put distortion in the inclusion graph, and just by taking ratios of these numbers in this special case of multimatrices. And so you have a sequence of matrices, a sequence of distortions. And in this case, you see immediately that here I'm getting the Fibonacci numbers. And so by this well-known relation with the golden ratio, the even limit is given by this matrix, which does happen to be equal to the standard. And so distortion, well, as you can check by by computing the Perron-Frobenius data of D. So in this case, it works, and I go into the standard distortion. Okay, for the A5, it works also. And this is the inclusion graph, this is the distortion graph, and you have a sequence. But the sequence is particular, is different from before. Namely, the even steps, the even jumps are all the same. So the even sequence is constant. So the limit is already achieved at the 0 level, so at the starting point. So I'm starting from the standard distortion. And what does it tell me? The difference of these two examples maybe has already convinced you of one of the inclusions of one of the implications of this theorem, so which is one of our good theorems in the paper. And namely here we characterize this Popa homogeneity that I described you before in words. So if we have an inclusion with all these properties, namely extremal essentially, and finite-dimensional centers, then the existence of an infinite tunnel, namely this homogeneity, is equivalent to, in particular, to the distortion of the inclusion being a standard. And now we have seen, of course, the implication that goes down is clear, because if you have an infinite tunnel below you, the distortion is a limit, and so it has to be standard by the theorem before. And we also show by using, in fact, also this characterization due to Popa that the condition is also sufficient. So if you are standard, then you have a tunnel. That's a non-trivial step. Okay, so now let me, given I still have some time, so well, give me, well, I will describe this condition here. So that's Popa condition for the existence of an infinite tunnel. And this is this condition says that I want the Jones projection of the Markov trace preserving expectation, so to have scalar center valued in trace. So that's the trace with values in the center of the basic so construction, and this is the condition that Popa wrote down. Okay, and by chance, so this is only for my personal fun, I think the homogeneity happens to be the same thing as a condition that we investigated in the paper with Longo, just for fun. So it happens to be the same as some super extremality that we defined and only studied for multimatrices, and which is I cannot even describe it to you because it's the coincidence of two states. One is the Markov trace, and the other one is a state that we use for describing the minimal expectation, for describing the minimal index that we call a spherical state. And it's numerically is just the equality of this. So this is the Markov trace on the minimal central projections in A equals the square of this Perron-Frobenius entry of D. Okay, and now I go back to the classification because now we are halfway done actually. Namely, if I add also hyperfinite and finite depth now, so which is once more the standard invariant is multifusion, then this is a complete invariant. So that's our theorem, or the theorem, the part of the theorem that I want to describe today. And what does it say explicitly? That the fact that two inclusions are star isomorphic is the same thing as having the same standard invariant, namely having the same, so having a unitary tensor equivalence between these two unitary multifusion categories and having the same distortion in this sense. And now, given I suppose my time is almost over, I just tell you that, so here where there is still work to do if you want, namely, on top of this, so how can we show this theorem? The ingredients that you for sure know, well, is one, the existence of a generating tunnel in the case of homogeneous, so when the distortion is standard. And the second ingredient is so what do we do if we don't have standard distortion? So in a nutshell, we introduce a notion of Morita equivalence for inclusions that is not categorical. So it changes, that changes distortion. And we have a formula to say how distortion changes in this way. In such a way, if you start from a non-standard distortion inclusion, you can go to a standard one, do the tunnel, and classify. And then in principle, I have also the definition of Morita equivalence, this formula that I told you in words, and the classification for representations, but I think that was what I wanted to say. So thank you for your time.